have a webinar on hands-on with Apache Iceberg. And with us, we have Alex. Alex is the head of DevRel at Dremio with an experience of a developer and an instructor. I think this is the best combination to learn from. His professional journey includes GenEd, Crossfield, Campus Guard, and many more. He also co-authored Apache Iceberg, the definitive guide, and we will probably have a link, for you all to go through the guide, because I'm pretty sure it's a good one for you to learn in depth about it. And Alex has also spoken on multiple events like Data Day Texas, Data Council. He's passionate about tech, sharing his experience with blogs, videos, and podcasts and whatnot. Thank you so much, Alex, for being here, for being a kind enough person to share all this information with us. Just a quick few things before we dive into the webinar. We will take all the question and answers towards the end of the webinar. Please feel free to pop in your questions. Second, we will have a few polls coming in on your way during the webinar. So please do answer them, because that will give us a direction as well, how to cater to the audience we have today. Alex, over to you now.
Hey, everybody. Welcome, and thank you for having me here today. But my name, again, is Alex Merced. I'm a head of DevRel here at Dremio, and here we're going to talk about just kind of getting more acquainted with Apache Iceberg. So let's continue on with the presentation. So during this presentation, we're going to talk about well, I want to introduce where I'm from. I'm from a company by the name of Dremio, which we are an intelligent lakehouse platform. So we'll talk a little bit about what that is and what that means, because it's very large and hard with leveraging Iceberg. But also, what is a lakehouse? Like, what's the point of this whole word lakehouse? And what is Apache Iceberg's role in this infrastructure? We'll go through some example transactions showing you sort of like Apache Iceberg in action, and then talk about the benefits of Apache Iceberg. But like I mentioned, I am one of the co-authors of Apache Iceberg, the definitive guide, and you can get a free copy by scanning this QR code here. So by scanning this QR code, you can download a free copy of the full book from O'Reilly. I'm actually working on 2 more books that should be available in their early release versions in the next couple months. So keep an eye out for that, all Iceberg related, and Lakehouse, and another project called Apache Polaris. So I spend a lot of time thinking about this space. So I'll leave that QR code there for another 2 seconds for anyone who would like to scan that QR code. And let's continue on. Okay, so I mentioned that I'm from a company named Dremio, and Dremio, we are a lakehouse platform. Essentially, the idea is, think of it as like a lakehouse in a box. And this will make more sense as we talk about what is a lakehouse. But basically, once you have your data in Apache Iceberg using tools like Hevo to land your data as Apache Iceberg, Dremio can kind of take it from there, allowing you to run analytics on that data, allowing you to accelerate that data, allowing you to catalog that data, and just basically handle all the bits. That way you can actually use your data lake, much like you would use a data warehouse platform, and not have to think about all the maintenance and all those kind of things, but still have that open access and lower cost point that you have with the lakehouse versus a data warehouse. So with that, let's explain what is a data lakehouse. And to appreciate what a data lakehouse is, we need to appreciate what we've been doing already. And when we think about sort of traditional data systems, we have they fall into 2 categories: either a database or a data warehouse. We oftentimes use database for applications, for like what's referred to as a transactional workload. And then we have data warehouses, which we usually use for like analytics and more analytical workloads. But bottom line is that these types of software, they do 2 things for us, or they do several things for us. And the beauty of it is we don't have to think about it. They figure out how we store the data. Okay, so when I store data in a Postgres database, I don't know where the data is stored or how it's stored and how does it all work. It just works. It handles what's called a table format. So that means, like, how do I understand that the data that I've stored this is the sales table, this is the orders table, this is that table. All that is handled by the system. Now, how do I know that there's a sales table, an orders table, and all these other tables? That's a catalog that tracks the tables that exist. And then there's a processing layer that allows me to write like SQL, take that SQL, turn it into an execution plan, and then execute that query. And all of this stuff is abstracted away to one nice piece of software. This is why we love using databases and data warehouses, because they just make it where we don't have to think about these things. And it's great when I'm doing transactional workloads, which is generally row-based data in a database, or if I'm thinking about analytical workloads, where I'm thinking of the data in a more columnar way in a data warehouse. But there's one big catch. every database, every data warehouse does all these things differently. So if I want to use two databases or two data warehouses with the same data, I essentially have to copy the data into both systems. And when you start talking about larger and larger companies that have lots and lots of different departments who will prefer different tools, then you start realizing you end up copying the data over and over and over again throughout the company, which leads to one, cost of storing all that data, two, costs of operating all these systems, and three, consistency issues where the data isn't consistent from department to department. And so there needs to be a solution, a way that we can have consistent data where everyone can use the tools that they want, but use it on the same version of the data instead of making many, many copies. Well, when we think about sort of systems that we have now where we can store that data, that sort of canonical copy of the data, we have something called a data lake. So you're using some sort of distributed storage layer. Think of like an object store like S3 or ADLS, or something like a distributed block storage layer like a Hadoop. But you're using some sort of distributed storage layer. And then you can use tools that can basically run queries against data on this layer. These are tools like Dremio, where I'm from, AWS Athena, etc., that allow you to run queries on Parquet files, CSV files, JSON files that are there. And this works. But yes, continuing on. Okay, so we have our storage layer. So the problem with like the data lake is that, well, I can run queries on files, again, like CSV files, JSON files, etc. The problem is like updating that stuff, you don't have the same kind of consistency guarantees that you get in a database and data warehouse, like ACID guarantees. You don't get you don't get a lot of the benefits. And on top of it, it's not necessarily as fast. It's not as easy to use. So in that case, it doesn't quite fit the bill of replacing a data warehouse. But what's really missing? When we think about it, we have the storage layer, we have the compute layer. What we're missing is a way to recognize different chunks of data as a table and a way to track those tables. So if we just add in those layers, a table format and a catalog, well, then you fix the problem. Now the table format's going to help answer the questions of like ACID guarantees and make it easier to do SQL. And think about it the way we use the data warehouse, where we think about the data as tables, not as a bunch of files, and make it much easier to use the data with the same sort of guarantees and ease of use that we're used to. So that's the beauty of the data lakehouse. You're basically taking the data warehouse, which is something we like because it's easy and fast, but move it over to the data lake, which is going to be much more cheaper and flexible, giving you that data warehouse feel on your data lake. Okay. Cool. Okay, and now let's talk about Apache Iceberg structure. Okay, so when we take a look at Apache Iceberg isn't like a software. It's not software that you run. It's a standard specification. It's a way you write metadata. It's a way you write files to your storage. But the structure of Apache Iceberg follows certain different pieces. There's a piece called the catalog. So the idea is there needs to be some sort of listing of your table, somewhere that says, okay, hey, I have a sales table, an orders table, all this. That's going to be the catalog. There's lots of different choices you have for what your catalog is. But when a tool like Dremio queries that Iceberg table, what it's going to do is going to go to that catalog first, and it's going to go to the catalog and say, hey, I'm looking for the orders table. Where is the orders table? And then the catalog is going to come back with an address where it can find the metadata for that particular table. So then that way Dremio can then go back to storage. Okay, so it'll go back to the storage, get that metadata file, which is referred to as metadata.json. And that metadata.json is going to have a bunch of information about the actual format. So like what's the schema, what's the partitioning scheme, what are the different snapshots of the table. And now Dremio from there can say, okay, hey, you want to create the newest snapshot, the newest version of the table. So in that case, it'll look inside the metadata and say, hey, where's the information about that snapshot, that newest version of the table? And that's going to go to point to a manifest list. Okay, basically, in this case, we're going to the newest snapshot. And that manifest list is a list of essentially all the files that are going to be part of the table at that point. So it's not really like a list of files. It's a list of groups of files. And each group of files is referred to as a manifest. And then based on this, now Dremio knows these are the files that make up the table, so only scan those files. But these metadata files also have information on those files. So that way, instead of me, because in the past, what you would have to do is you'd have to open up every file. So Dremio would have to go open up like thousands of files, and it would take forever. But with Iceberg, I can look at the metadata and say, okay, hey, this file doesn't have information I need. This file doesn't have information I need. And then I can skip those files So out of a table that has 100,000 files, I might only end up scanning 1,000, resulting in a much faster query. And that's the beauty of Iceberg, that you have all this metadata that allows you to kind of really trim down the time it takes you to scan storage systems like this. This is essentially how data warehouses work. But again, it's all abstracted away, and every data warehouse does it differently. This creates an open standard way that every tool can use, because the standard is open. And basic tools like Dremio, AWS Athena, Trino, etc., can all adopt the standard, allowing you to use whatever tool you want. So like nowadays, like pretty much every tool supports reading and writing Iceberg tables, allowing you to kind of use what you want with the same sort of version of the data. So they'll kind of see an example of how this works in action. And then also at the end, I'll show you some tutorials where you can actually get a hands-on your laptop, spin up a little environment on your laptop and actually run some queries and see the files in storage and actually see this whole thing. Let's create a table. So in this case, I'm running some SQL that creates a table. So I'm just creating a table. There's my schema. And then I'm partitioning the table. I'll talk more about partitioning in a little bit. But bottom line is right now, all I'm doing is creating the table. So there is no data. So there's no data files. The only thing I'm creating is a metadata file that describes the table, the structure of the table. And then I'm telling the catalog that, hey, guess what? There's a new table called db1.table1. And the location of that metadata file is this address on S3. So see, it literally looks like this. db1.table1 points to this address on your storage. And that's all the catalog is doing. It's just saying, hey, this table, location here. This table, location here. This table, location here. So right now, my storage looks like this over here. So I have a folder called table1, that's my table. And in that folder, I have a metadata folder with all my metadata files that describe the table. And then all my data files, the Parquet files with the actual rows of data. So now if we insert into the table, okay, we have db1.table1. So we're inserting a record. So now I do have to write data. So first thing I'm going to do is, and again, this is like Dremio who does this, not you personally. That's the beauty of this. I just write the SQL and then the engine does all the work. So in this case, I write the data file. So Dremio would write the data file. Then we would have to track that data file. So that would be the manifest. And then we're saying, hey, there's a new version of the table, a new snapshot. So we have to create a manifest list for that snapshot. So we would create the manifest list, but that snapshot has to be inside the metadata file. So we create a new metadata file. So this new metadata file has the old snapshot and the new snapshot. And then we tell the catalog, hey, going forward, don't point to the old metadata file, point to the new metadata file. So as you can see here, the reference has changed. And now we're pointing to the new metadata file. This is how you end up having like asset guarantees. Because technically, you're not updating the catalog until you've done everything else first. So in that case, if something goes wrong in between, the catalog never gets updated and you're still pointing to the old snapshot, which is fine. So the only way catalog is going to get updated is if the transaction was successful. Thus, you have atomicity, meaning the transaction either succeeds or it doesn't. You're not going to end up getting half-baked transactions. Okay, so if you see here, we take a look at the update of our storage. I can see my metadata folder. I have my metadata.jsons. I have this snap avro file. That's going to be my manifest list over here. And then I have this other avro file, which is my manifest list listing the individual files. So this is the metadata that tools like Dremio leverage to efficiently scan the data. And then again, I actually have the data itself stored in a Parquet file. Cool. So again, when you're using a tool to write Iceberg tables, so something like a Hevo or any kind of ETL tool, this is essentially what it's doing for you. And basically, it's just going to update the table, create all this metadata, write it to your storage, and then you can use a tool like Dremio to then query that data. Okay. Now, another cool feature that Iceberg has is this ability to run like merge transactions, which are upserts. So essentially what we're doing here is we are going to merge the table one with another table that's our staging table and say, hey, you know what? The staging table has some new data. Some of the data is really updates to existing records. Some of the data are new records. So I can say, hey, let's merge our table with this staging table, match both tables based on ID. So basically we know if the two records in the two tables have the same ID, then they're the same information. We're just updating, not inserting a new record. So when they match, we update. And then when they don't match, we'll insert the new record. That's a new record. So I can express that in SQL. And again, all the beauty of this is that this is all happening on my data lake. So this is not like a separate data warehouse system that has its own storage you have to pay extra for. This is all happening on your data lake, your S3, whatnot, and you're paying that lower cost of storage. And again, using whatever tool you want. That's the beauty of all this. But in this case, what's going to happen is that the engine will determine what new files need to be rewritten. It's going to write the new files, then write any manifest it needs for those new files, then create a new snapshot, so a new manifest list, create a new metadata file that now has all 3 snapshots listed inside of it, and then update the catalog and say, hey, going forward, catalog, point to the new metadata file. So that way, again, the catalog becomes a source of truth on what's the right version of the table. So you have the historical versions, but you always know what the current version is. So as you can see here in my storage, I got my metadata folder that has all my data stored, and I can start seeing that in my data folder, and again, we did partition the table, which means we said, hey, when you write the data, separate the data based on a certain value. So in this case, based on a timestamp. And you can see it's separating that out physically in that data folder. So the files for certain timestamps are in a different folder than others, which allows it to scan it more efficiently for future scans. And we'll show an example of that. So let's just do it now that we've written and added data to the table. Let's actually read the data in the table. So now, if I read the data, so I just run a standard select star from db1.table, what it's going to do is that Dremio or Trino or Snowflake or whatever engine you're using to read the data, okay, it's going to first go to the catalog and say, hey, catalog, I'm looking for table 1. Catalog is going to say, hey, here's the metadata file. Okay. And since I didn't specify like a particular snapshot, it's going to assume I want the newest snapshot. So here's the newest snapshot, which points to this manifest list. And then from there, Dremio can be like, okay, hey, all the manifests are needed, and all the files in those manifests are needed because it's a select star query. So in that case, all the data files will be scanned. And then again, this is going to list which of those individual files, so that way Dremio can then go scan them from your storage. Okay. But for me, it just feels like a normal running of a query on a data warehouse with very similar speeds, if not sometimes faster, depending on the tool you're using. Now let's do a more specific query. So in this case, we're going to do a select star, except we're actually going to filter based on that timestamp. And as I mentioned earlier, that timestamp is what we're partitioning based on. So because of that, the metadata actually has this partitioning information and says, okay, hey, these are the files that have this value, these are the files that have this value, and so forth. So now Dremio will do the same thing. We'll go to the catalog and say, hey, I'm looking for table 1. I'm going to go to that newest snapshot. But now when I get to the manifest list, I can see those groups of files. And those manifests, each of them are written with a particular like partition value. So it'll know which one has the right data based on this particular query. And then from there, I can then say, hey, even though there's all these files, like these 2 files are both part of the snapshot, I really only need to scan this one. This is the only one that actually has a value that's within my particular filter. Okay, so in that case, instead of scanning 2 files, I'm scanning 1. Now imagine that with like 1,000,000 files, where I can scan 1,000 files instead of 1,000,000. That's going to really increase the performance of your query. Okay. Cool. So that's how that would work. But an extra special feature is something called time travel. So remember, in our metadata, we've been tracking all the historical snapshots. So I can actually say, can you scan one of those older snapshots? I don't want to scan the current version of the table. I want to scan an older version of the table. I can sit there and say, hey, as of, and then specify a particular timestamp. And then what it's going to do is that when it gets the metadata file, it's going to say, hey, is this snapshot before that time on or before that timestamp? Nope. Is this snapshot on or before that timestamp? Yes. So in that case, it'll go to this snapshot, which will point to this manifest list, not this one. And so basically it's going to go down a different path and only identify the files that are part of that version of the table, allowing it to scan that version of the table. Okay. And so in that case, now this is wonderful because now I can now compare last month, how the data was like a month ago from the way it is today, and do these kind of like have this kind of auditability. Like you can have this in a data warehouse, but oftentimes it gets really expensive because you don't realize how it's managing. Like you're physically storing all those copies of the data. So you may have like a 1 GB table, but be storing like 100 GB because you have every historical version of the table. But the storage on your data lake is going to be much cheaper for storing all of that than your storage in a data warehouse. So you get that feature without the big cost associated with it, which is what oftentimes is driving like your data warehouse costs, having all that sort of historical versions of the data. Okay, now let's kind of summarize. So now that you've seen like sort of how Iceberg works, so like how basically having this metadata standard allows engines, and again, the cool thing is that that whole pattern that I talked about is a standard, it's a specification. So any tool can leverage that specification. So pretty much again, nowadays, most tools will leverage the ability to read and write to Iceberg. So if you have so if you're a big company and one company, one department wants to use Dremio, another department wants to use Trino, another department wants to use Star Rocks, they can all use it with the same data. You're not duplicating the data into each system. And on top of that, you're going to get consistency. So when all three teams using different tools are querying that data, they're querying the same version of the data. And when they change that data, no matter which tool they're using, you have asset guarantees. You don't have to worry about half-baked transactions. It's just going to work. It's kind of like if everything was part of the same database system, but they're really all a bunch of different pieces of software that are just using a standard to help coordinate. You have schema evolution. This is something that was lacking in just a standard data lake. Because when you just had like pure Parquet, CSV, JSON data sets, if you wanted to change like the pattern or the schema of the data sets, you pretty much just have to rewrite the data sets. So in that case, that would be really expensive to update the schemas. Another reason why people would use data warehouses. But now with Apache Iceberg and data lakehouses in general, you have schema evolution, where the schema is tracked in the metadata. So even though some data files might be written with an old schema and some data files might be written with a new schema, the engine knows what's the current schema based on the metadata, and then can make sure that the output matches the current schema of the table. Again, you get that improved performance. Now you get data warehouse-like performance on your data lake queries because the Iceberg metadata allows you to say, hey, all these files are part of the table, but based on the metadata, I really only need to scan these files. Okay. And then so all the features I've talked about so far are standard lakehouse features. So whether you're talking about Apache Iceberg or other formats like Delta Lake or Apache Hudi, you're going to get time travel, you're going to get consistency, you're going to get asset guarantees, you'll get all that. But there's a couple of features that are unique to Apache Iceberg. Partition evolution is one of them. So in this case, not only can you change the schema of the table, you can change the way the table is partitioned. This can only be done in Iceberg. And the cool thing about this is that, sometimes your needs change. So oftentimes in the past, if you were ingesting data and partitioning it by month, and then later your data velocity increased and you wanted to shift over to partitioning by day, you'd have to rewrite all the data, okay? Because basically you can have a partitioning scheme. So you're rewriting petabytes of data just because you need to adjust for your new velocity. Well, we don't have to do that with Iceberg. I can be partitioning by month where it makes sense. And then once it makes sense to switch over, it's just a change in the metadata. And then all writes going forward will use the new partitioning scheme. And the metadata will tell you, okay, hey, these files were written with this partitioning scheme, these files were written with these partitioning scheme. So that way the engine can understand and plan the query correctly and not have to worry about rewriting the entire data set just because you changed the way you're partitioning the data, which is, again, a huge time saver and a huge cost saver when you're trying to figure out how to get your partitions right. Also, this hidden partitioning. So in this case, the Iceberg metadata allows you to specify certain like functions or transforms on your partition value. So instead of you having to create like a separate month column or separate day column or separate hour column and then store that in your data, you can actually say, I want this table to be partitioned based on day, month, hour. And then when the data is written, it actually saves the transformed value ranges in the metadata, not the data files. So the engine can use the metadata to figure out, hey, which files belong to what partition without you having to store the extra data in your Parquet files, which makes the data engineering work much easier. But on the same time, it also is good for the analyst because now the analyst doesn't have to track multiple columns. They can just say, hey, give me the data between this timestamp and that timestamp. They don't have to do something like between this timestamp and this timestamp and this month and this month and this day, which used to be the case in the past, where you had to write these really complex queries because you had these partition columns that you want to take advantage of. So this makes taking advantage of partitioning and having less accidental expensive queries that run a really long time, much less likely. So you get easier partitioning that not only makes life easier, but also saves you money. And at the end of the day, wherever you can cut costs is always nice as far as like driven costs of just executing all these things. Okay. Oh, and then, oh, okay. Well, what I'll do is I will send some links over to Radhika where you can find some exercises where you can try this stuff out on your laptop, so that to
Yes.
send out in the follow-up email.
Yes, I will do that and I'll make sure that everybody gets those. Thanks, Alex, for the whole overview of Apache Iceberg. I think everybody does have a lot of questions already. So let me just, go through them one by one and shoot it out to you. So we have a question which asks, does manifest have pointers to files essentially?
Okay, yeah. So basically the way it works, everything's like a file pointer in a sense. So the catalog points to the metadata file. The metadata file will point to the manifest list or the snapshots. And then each snapshot will point to different manifests or groups of files that make up the table. And then those will point to the individual files. So basically it's all the sort of like tree of pointers to help the engine discover what are the right files to scan for a particular query.
Okay. Cool. Hope that answers your question, Sri. We have another one from Sri itself. What would happen when you query using a data range? How does Iceberg now the delineation of old partitioning schema versus new partitioning schema? How does it impact the performance?
Um, One, theoretically, I mean, it's generally going to improve performance because you're like, well, here's what happens as far as like the actual query planning. Every manifest is going to have like has a particular partition value that it was written based on. So when you're in the manifest list, with the list of the different manifests, it'll actually say, hey, this manifest was written with this partition value, this manifest. So in this case, right there, an engine can start saying, okay, this manifest I don't need, this manifest I need. But also it says not only what the partition value is, it says what the partitioning scheme is. So let's say you had evolved the partitioning scheme. So I have partitioning scheme 0, you have partitioning scheme 1, partitioning scheme 2. It'll have that number there. So then Dremio would know, okay, hey, this manifest was written with partitioning scheme 1, so that's how I should think about it. And it can then reason that out appropriately. Now, again, there are still things you probably wouldn't want to do in practice. Like, let's say, like the examples I've given so far are based on time values. So with time values, it's pretty straightforward. Now, imagine like there's like a voter data set, and then I'm partitioning it based on county, and then I start partitioning it based on political party, and I don't go back and rewrite the old data. That can affect performance. That's more of a data management issue, because now I have a portion of my data. Like if I have a query that comes in by county, the portion of the data that's partitioned by county is going to be much more performant to scan than the portion that isn't. In those kind of situations, this is where like newer technologies like clustering make a lot of sense. So this is actually a feature that Dremio just released where we're doing like essentially clustering for iceberg tables. So instead of partitioning and separating the data physically, you can specify a partition key, and we can better sort of like batch up the data to different files, without creating those hard lines for optimal read performance. But those are just things like are based on different query patterns. Now you're starting to see much more like a room of like different companies offering different table services where they're offering their own algorithms where they'll help figure that out for you. They'll assess your query patterns, then take a look at your data files, and then rewrite those data files based on that for optimal execution, and without having to be overly reliant on partitioning.
Got it. We do have a lot more questions. So, Alex, would the latest manifest files contain pointers to all data files or only the files which has changed in that recent change?
Yeah, so if I wrote a new manifest, like if I just added data, it would just be a new manifest file that refers to those new data files. And then the manifest list would have a list of the old manifests and the new manifests that are relevant to that data, to that particular snapshot. So it just depends on what the particular change is, but it'll always make sure that the right manifests are listed in the right manifest list or snapshot.
Got it. How to manage the snapshots? I mean, to remove the files for versions I don't want to keep.
Oh, so basically there's two ways to do that. There's a procedure that's built into the Spark libraries for Iceberg, where basically you can specify a date and say, hey, I want to expire any data older than, let's say, 7 days. So then it will expire those snapshots and validate them. And then it'll determine, hey, these are the data files that are no longer associated with a valid snapshot, and then delete those files for you. So in this case, generally you should never manually do that, because you can generally never manually play with the files, your Iceberg files. Always let the tools handle that. And again, it'll just feel like a normal data warehouse. But, again, that requires you to kind of run Spark and then have to do that manually. Nowadays, more and more companies are offering table services. Usually this will be paired with whatever you choose as your catalog. So for example, if you're using Dremio catalog, we would handle that for you. So you would set some like data retention rules, and then periodically we'll just go back and expire those snapshots, clean up those data files based on the rules that you set. And then you don't have to worry about that. But there's more and more offerings that offer stuff like that. Usually it's attached to the catalog.
We have another question which says, if we want to run a query against a certain time range, is there handling of schema changes within that given time range? Can you have a snapshot of data that contains records with different schemas?
Yes. So basically what happened, like in the Iceberg documentation, it'll tell you sort of like, hey, which schema changes are allowed. Okay. So generally there's going to be certain schema changes, because it has to be able to kind of retroactively and sit there and be able to superimpose the change on the old data. But for example, if I were to change like a number field into a text field or something like that, it can do that. So basically the engine would just read the data and then transform that older data on the output into sort of the new data format. And again, what are the specific sort of changes? Usually, like, different types of numbers, like whether if you need like a more granular number, like going from like just an integer to like a long or something like that. Or if you rename a field, so because what's going to happen is in the metadata, each field is going to have like an ID number. So if I change the name of the field, it may have a different name in different data files. The ID number doesn't change. So it'll know that, okay, even though they have different names, this is the right same data. And then again, you'll get the output with the right schema based on the snapshot that you're using. So if I query a snapshot from today, it's going to use the snapshot or the schema for that day's snapshot. But if I scan the data a month ago, which had a different schema, it'll make sure to use the version of the schema for that version of the data. So every snapshot will actually have a listing saying this is the schema that was active at the time. And so that way the engine can then make sure to transform the data, the output to match that.
We have two more questions. Can I understand more about what the catalog is doing at Iceberg layer?
The key thing that it's doing is that it's really just essentially like a map. So it's a map of here's the name of the table to here is the location of the metadata. It doesn't really do much other than that. Nowadays, catalogs are doing more. Because since every tool has to interface with the catalog to discover the tables, people have realized that this probably makes sense to be where governance happens. So now you're starting to have projects like Apache Polaris that are creating catalogs that have a governance layer. So now what I can do is I can create users using Apache Polaris and say, okay, hey, that user only has access to these tables. So then when they use whatever tool they're using, they would connect the catalog using their credentials. And then when they go to request a table, they can say, okay, hey, well, that credentials doesn't have access to that table, so it'll reject the request. And that way, whether I could be using 5 different engines, all the engines will have access to that same user will have the same level of access regardless of which engine they're using. So catalogs are becoming that place for portable governance. And Apache Polaris has been kind of leading on that particular journey.
Awesome. The next question, could you explain how deletes work in Iceberg tables?
Oh, yes, that's a fun question. Okay. So there's generally when you're just doing SQL, you're just doing soft deletes. By default, Iceberg tables are going to be copy on write. So for example, if I delete a file, if I delete a record, I don't actually delete the data. All it's going to do is let's say that data file, that record was in a data file that has 1,000 records. It'll just rewrite a new version of that file that doesn't have that record. So now there's a new one that has 999 records. And that new file is part of the new snapshot. the old file is not part of the new snapshot, but the data file still exists. So the data hasn't been deleted yet. Now, this is where snapshot expiration becomes important. When you clean up the old data and you invalidate snapshots, that's when the actual physical data files get deleted. So there's a question of, hey, am I deleting it from the version of the table versus do I need to, like, for example, for like things like GDPR, you might really care about, hey, is it physically deleted from my storage system? And that's where like the snapshot expiration and having good data retention policy, clear data retention policies is really going to matter. So that way you make sure to set those policies for whatever system you're using to clean that up effect the way you want. But as far as like just deleting the record, it would just be a normal delete SQL command. And again, all it's going to do is just write a new data file without that data, and those new files become part of the new snapshot. Data files only get deleted when snapshots they're associated with get expired.
Got it. There's one more question. Is there overhead in data retrieval as it has to go through catalog, then metadata, then manifest, and then actual data?
I mean, theoretically, there's overhead, but I mean, the same thing's going on in a data warehouse. Now, of course, these are decoupled components. So of course, there's always going to be optimizations you can have when you couple them. But depending on which, and again, depends on which tool you're using. A lot of those things are pretty addressed, and sometimes they are pretty coupled on the system you're using. For example, like nowadays in the current incarnation of Dremio, you can use other catalogs, but we also have a built-in catalog which we're able to optimize for. But usually, you're not any kind of latency that would cause is almost non-existent. And then the beauty of it is because you're using a data lake, you're using like object storage, it can scale infinitely, and you can scale infinitely across multiple tools. So you're still getting very, very, very performant table scans, but you're also getting that flexibility you get with being able to operate off your data lake. So you're not, again, people now can use different tools, but people can scale those tools infinitely because you're not basically object storage will manage any replication of data and accessibility to that data.
Awesome. So you mentioned that about copy on write, but how merge on read works in Iceberg tables?
Someone's been, okay, good question. Okay, so merge on read, the way it currently works, it's about to change, is we use something called a delete file. Now, a delete file works in two different ways. It could either track the specific row in a specific file that's been deleted, or it tracks a value that's been deleted. And the beauty of this is instead of me rewriting the data file, so instead of rewriting those 1,000 records minus the record that was deleted, I could just write this delete file that says, okay, hey, just ignore the row 800. The beauty of this is that at write time, I can write a lot faster because I'm not rewriting 1,000 records. I'm writing one record in a delete file. So much faster for write time, but it affects read latency because now at read, the engine has to go, oh, wait, I read these 1,000 records, but I need to ignore one of them. Which one is it again? So now I got to go read this other file, and then I got to reconcile that. So there's a cost. So basically, there's always a trade-off. If I want to save time on writing, I have to pay a cost on reading. So usually the way you kind of manage that is you have regular compaction. So your maintenance of your tables, if you're having a lot of this, you're gonna want that to be more regular, because when you maintain or compact your tables, it'll actually clean up these delete files. So essentially, for example, in a streaming use case, I might be streaming data every hour using merge on read if it has a lot of updates in that streaming jobs, because I need to have it be really fast for streaming. But again, every hour I'm going to be generating a lot of small files, and then also these delete files from all these updates. So what I want to do is maybe set up like a compaction job for every hour, just clean up specifically the data from the last hour. And then that way, at the end of each hour, especially if I partition the data by hour, I would want to kind of like run that compact, because then I'm running a smaller compaction job that's going to run a lot quicker. And I'm optimizing data that's never going to need to be optimized again, since the partition is an hour. So again, it just depends on sort of like, hey, how are you partitioning the data? How quickly, what is your data velocity? And what are your SLAs to determine sort of what the right cadence is for maintenance? Again, there's more and more tools becoming available to kind of just abstract that part away. But again, still a lot of people will manually do it currently, as again, the tools to abstract that away are still fairly new. And people are learning about them and assessing the different ones and things like that. But yeah, merge on read, essentially you have these extra files, go to lead files that kind of make that possible.
Wow, I think the questions are never ending this time, and we have already answered around like 10 questions. We have another two more. So we'll just take these two, and if anybody has any other question, we can definitely route it through Alex for sure. We'll make sure to, put a link where you can get all the questions answered. So the next question is, since delete needs rewriting the entire data file, would that mean that delete would typically be costlier compared to, let's say, insert or an update?
Yes, I guess. Because yes, you're right. On a delete, you're creating a delete file to ignore the old file, and then you're creating a new data file for the new version. Well, no. An update would be more expensive because in a delete, you're just writing a delete file. So you're just saying, okay, hey, ignore that record. But with an update, you're doing both. I'm gonna like in merge on read, I'll create a delete file to ignore that old version of the record in an old data file, and then creating like a new Parquet file with like just that new record. So I'm doing like both those things in an update, merge on read style. But again, depending on the nature of the actual individual updates and deletes, they can be more or less expensive. But again, I don't think it would be much. And generally, ideal world for like most of this stuff, it's not going to be the same level of like updates and deletes that you would expect on sort of your transactional systems when you're talking about like your front end applications. Because again, Iceberg is not meant to be your transactional system store, but your analytical system store. Now, of course, especially with like streaming data where there might be, like late arriving data, things like that, there'll be changes, but it's all manageable. There's different ways of managing it.
Got it.
But yeah, I haven't seen it be too much of a problem. But usually, again, you'll want to figure out what the right cadence for optimization of the data is.
Yeah, I think one thing that I have taken out from all of these questions is optimization is becoming bigger part than knowing how to use Iceberg. So we should
100%.
definitely plan something over that as well. Um, One more question, is Iceberg good for streaming use cases? My understanding is it is not optimal for streaming use cases.
Oh, no, it is, and it's gotten a lot better. I mean, you have companies like Confluent that just introduced features like table flow, and Red Panda's introduced a similar feature. A lot of companies are really creating really solid. Upsolver, before they were purchased by Click, created some pretty solid like streaming stuff for Iceberg. So it's becoming more and more of a thing, and companies are, not only do they optimize for it, but they actually contribute to open source to help improve the streaming story for Iceberg. So there's people who do it, and they do it just fine. Now, the story will get better with a lot of the changes to delete files. We're going to move over to deletion vectors, and other changes are going to come down the road. That story becomes better, but people are streaming with really low latency to Iceberg already. Whether they're using services again, like I mentioned, Confluent, the Red Panda, or they're using things like Flink and Apache Kafka Connect directly. It's Iceberg generally is a very good general use case. Like it's pretty good at everything. It doesn't specialize in anything specifically. Like you take a look at like a format like Apache Hoodie, where it's more really specifically tailored for streaming ingestion. But then again, what happens is that you then have to convert the data over to something else oftentimes for reading, whether it's Iceberg or Delta. So then you kind of lose a lot of the time you save having to convert the metadata versus having sort of something that works pretty well kind of throughout the whole pipeline, end to end. But yeah, no, I mean, the streaming use case for Iceberg is there, and it's gotten way better over the last few years with a lot of the contributions from many different vendors to library like Flink and Spark specifically for Iceberg purposes.
Awesome. So I'll give it just one more minute for people to ask their questions. We do have some time left. If you guys have any last questions, please feel free to ask. And we have launched another poll, which basically gives us a feedback that how did we do today and how can we make it better. So please answer to that as well. Yeah, I think it was pretty insightful, Alex. Um, so I I think we have 10 other questions from Shri, and we'll have to have a separate session for that, which is pretty true. And I think we can keep a follow-up session as well. And Shri, please feel free to connect to Alex over LinkedIn. what we can do is while we are dropping up the recording, we'll drop up Alex's ID as well. So I think Alex would be really, the best person for you to answer all of these questions about Iceberg.
For sure. Definitely follow me on LinkedIn and on X and Blue Sky. Constantly posting stuff. And again, sorry for some of the noise earlier. I like how like all the noise stopped I finished the presentation, but it is what it is.
Yeah, I think you taking out time is pretty great for
Mhm.
us, and we'll definitely make sure that we keep on having such sessions where you also get to interact with people and people also get to know a lot more about Iceberg, which is I've been seeing it's all over the internet and all over the data space. Thank you so much, Alex, for joining in. Thank you, everybody, for attending in. We'll make sure to give you all the links, all Alex's LinkedIn ID, and even the recording for this webinar. Thank you so much for joining.